Hello and welcome to Team 8's final presentation for the analysis and redesign of a Luxo desk lamp. Desk lamps are used to supplement workspace lighting and provide additional illumination for visibility during tasks. Our primary customer group we are targeting are businesses who purchase the desk lamps for desk and office space. The secondary customer group we are targeting are individuals who purchase the desk lamps for home use. In the exploded assembly shown, there are 31 different components and 19 different part numbers. In the subassembly view, we have a bottom arm, a middle joint, a top arm, and a lamp.
For our functional analysis, we determined the main function of the lamp to be lighting objects, with subfunctions of directing light and providing light, each with their own respective subfunctions. To assure dependability of the lamp, we determined that it needs to prevent overheating, and in order to enhance the product, we determined that we needed to control its brightness, adjust its height, and adjust its angle.
So here is the function component mapping matrix for the lamp. On the far left, we have the components of the lamp, and on the top, we have the different functions from the previous slide. The X's show which components perform which functions. A component can perform multiple functions, and a single function can be performed by multiple components.
For the product family design, we split our functions into which would be the same and different for both customers. As you can see, how the weight is supported and distributed will stay the same for both variations, as well as how the power, airflow, and brightness are handled. The main difference between the variations for primary and secondary customers is the adjustability. We plan to have the product design allow adjustability in height and angle, while the secondary design has no real adjustability.
Continuing with product family design, we split up the different components of the lamp into two categories: platforms, which would be the same across customer groups, and modules, which would be different across customer groups. Under modules, we included everything that comprises the arm itself, whereas under platforms, we included the lamp base, shade cover, bulb, and neck.
The common interfaces of the two different designs can be shown here. These are mainly the connection between the arm and the base of the lamp, and the connection between the head of the lamp and the arm. This is how the two arms can be essentially exchanged out with one another in manufacturing as needed.
Our original assembly sequence consisted of a ground-up approach, beginning with the lamp base and assembling up the arm of the lamp into the lamp head. To delay differentiation, we realized that we could assemble the lamp head first, as this process and the corresponding parts are the same across product groups. By doing so, we were able to delay the differentiation by 2 assembly steps, additionally reducing the total number of steps by 2. Due to the large differences between the primary and secondary designs, however, delayed differentiation is limited for this product. For design for manual assembly, we made changes to a platform and module of the original design. The platform we changed was the lamp base. Originally, the lamp base was attached to a linkage arm for both designs with the pin. We modified the base of the lamp to include a small extrusion, removing the need for this pin and following guideline DfAS1, or minimizing part counts. The module subassembly we changed was the bottom half of the linkage arm. We modified the connecting plates from the original design to be one piece, following guideline DfAS1, or minimizing part counts. Additionally, we added a slit to the plate to facilitate orientation using guideline DFPH2. Finally, we added a slit to the linkage arms to also facilitate orientation, again following the guideline DFPH2. These changes resulted in a reduction in assembly time by 59 seconds and increased the overall efficiency from 14.06% to 14.8%.
With regards for design to automated assembly, I chose the lamp neck platform subassembly. So my 3 main changes are shown on the right. First, I took the 2 plates and I combined them into one part based on DFAS1, which is to minimize part counts. The gap left in between the 2 sides of the plate are enough for the new flats that I created on the lamp neck itself. I created those flats based on DFPH2, which is to add features to facilitate orientation. So now the lamp neck slides in and you don't have to deal with trying to line up the hole on the rotating lamp neck with the holes in the plates themselves to insert the bolt. And sticking with the theme of the bolt, based on DFPI1, which is to add features for easy insertion, I did chamfers to the holes, so now the bolt does not have to line up perfectly because the holes are angled in. It should make it much easier to actually insert the bolt. Now, as you can see here, we dramatically decreased the cost of the subassembly as a whole. We cut out a part by combining the 2 plates, as mentioned on the previous slide. We saved the most money through the reduction of the handling costs of the lamp neck and the bolt, and the insertion costs of every part, except for the nut, because the nut remains unchanged, as well as saving a lot of cost in combining the top plate, so we don't have to double the handling costs and insertion costs of having 2 plates. In the end, both the handling or feeding cost and the insertion costs decreased, which means the total subassembly cost decreased by about 57 cents or 16%.
The 2 parts that were chosen for process selection from design for manual assembly were the connecting plate and the link arm. You can see the key dimensions of the connecting plate in the picture. The critical dimensions for product functionality are 8mm wall separation, since the link arm will need to slide in there for manual assembly, as well as the distance between the holes, which can be seen on the hole chart on the bottom right, since it's important that all the holes are aligned. The tolerances for these dimensions were chosen to be 8mm plus or minus 0.4mm for wall separation, and plus or minus 0.3mm for the distance between the holes. You can see the key dimensions for the link arm here. Critical dimensions for functionality include the 8mm side, since the link arm must slide into the connecting plate for assembly, as well as the distance between the holes, since the holes must be aligned for easy assembly. Tolerances were chosen to be 8mm plus or minus 0.4mm for the side, and 0.3mm for the distance between the holes. These tolerances will give us the precision we need without more expensive precision instruments. Here you can see the selection table for the two parts. The bolded items in green are the manufacturing processes that work within the specifications, and the one with the box around it is the recommended choice. For the link arm, the simple design of the part as well as the ability to order square stock that matches our needs makes conventional machining the winner, since all that's needed is 3 holes and a small notch. For the connecting plate, since it's a relatively more complex part, die casting was recommended. However, we recognize that a large patch size of around 100,000 units is necessary to make up for the high initial costs.
With the processes selected for manufacturing done, a cost estimation for the first part, the link arm, could be made. Since this part is to be made using manufacturing from a stock part, a cost estimate based on machining was made with a cost of $2.06 per part. However, a few redesigns were needed to make this part more manufacturing and dimensionally friendly. The first redesign was based on DfM-C3, which is used standard dimensions. Since this hole is unthreaded and meant to house an M2.5 screw, this hole should be a close-fit clearance hole, which requires a diameter of 2.65 millimeters, as opposed to the 2.5 millimeters it was previously. This standard dimension will hopefully make tooling for this feature easier. The second redesign was based on DfM-C4, which is design holes to tool shape. Since this slot is being milled, it would be extremely hard to get a straight internal edge as specified by the model. Changing these edges to be circular to fit the tool shape makes it more realistic to machine and reduces machine time cost. The third redesign is based on DfM-C6, which is to avoid long, narrow holes. The slot shown is meant to facilitate proper orientation when assembling. This is fine, but having a slot this big and long is excessive and leads to more machining costs. Shortening this slot allows for a reduction of machining costs and still allows for the facilitation of the part orientation. These redesigns gives an updated part, shown here, which is much more feasible to make and machine properly. On top of that, after a recalculation of the cost estimate, the new part is also 5 cents cheaper at a price of $2.01 per part.
During process selection, it was found that die casting was the better manufacturing process for the connecting plate as opposed to machining the part. After using a cost estimation model, the cost of manufacturing per part using die casting was found to be $1.21 per part. The part was then redesigned using Design for Die Casting guidelines. The redesigns consisted of the addition of drafting was according to DFDC Guideline 3 to help with the parts released from the die, the elimination of sharp corners according to DFDC Guideline 4 to increase strength, and the elimination of side pins to simplify the die according to DFDC Guideline 6. Because of the simplicity of the cost estimation model, the only redesign that affected the cost was elimination of a side pin. The new cost per part of the redesigned connecting plate came out to be $1.13 per part. Here we see an isometric view of the original part on the left and the redesigned part next to it with the added draft angles. The front view of both designs help illustrate the side pulls and sharp corners that were cut out in the redesign.
The product service system for the desk lamp will be a smart bulb included package where the customers receive the lamp and 2 energy-efficient LED bulbs to save money on electricity. The purchase will contain packaging to return any dead LED bulb, and the spare can be used to swap it and avoid any downtime. The bulbs will be provided at lower cost than standard retail or online suppliers, and our LED bulbs returned to us will be sent to proper repair or recycling facilities to minimize our eco footprint. The customer will receive a new LED bulb to replace their old one, and they will never have to go shopping for individual bulbs. From the customer perspective, they save time with the convenience and they save money.
The overall benefits of our work were reduced manufacturing and assembly costs, as well as a reduced assembly time by 59 seconds or a 16% decrease. After looking back on our design, we noticed that we have a suboptimal mass distribution as the lamp is slightly top-heavy. Some further improvements we could have made given more time were a feasibility study on the PSS plant, a targeted DFM on other components, as well as DFA on other subassemblies of the lamp. Upon reflection, we should have selected a less complicated original design as the lamp incorporated a very complex linkage mechanism, and we could have selected a larger lamp with greater sales potential as the lamp is relatively small. Thank you for your time, and I hope you enjoyed our presentation.